In Part 7 of Lecture 4, we discuss threads in Android. An Android application is the software that implements an app. Each Android application consists of one or more instances of one or more of four types of application components. Each component performs a distinct role in the overall application behavior, and each component can be activated individually within the application and even by other applications. The following are the four types of components. Activities. An activity corresponds to a single screen visible as a user interface. For example, an email application might have one activity that shows a list of new emails, another activity to compose an email, and another activity for reading emails. Although the activities work together to form a cohesive user experience in the email application, each one is independent of the others. Android makes a distinction between internal and exported activities. Other apps may start exported activities, which generally include the main screen of the app. However, other apps cannot start the internal activities. For example, a camera application can start the activity in the email application that composes new mail in order for the user to share a picture. Services are typically used to perform background operations that take a considerable amount of time to finish. This ensures faster responsiveness for the main thread, also known as UI thread, of an application, with which the user is directly interacting. For example, a service might create a thread or process to play music in the background while the user is in a different application, or it might create a thread to fetch data over the network without blocking user interaction with an activity. A service may be invoked by an application. Additionally, there are system services that run for the entire lifetime of the Android system, such as Power Manager, Battery, and Vibrator services. These system services create threads inside the system server process. Content providers. A content provider acts as an interface to application data that can be used by the application. One category of managed data is private data, which is used only by the application containing the content provider. For example, the Notepad application uses a content provider to save notes. The other category is shared data, accessible by multiple applications. This category includes data stored in file systems, a SQLite database on the web, or any other persistent data storage location your application can access. Broadcast receivers. A broadcast receiver responds to system-wide broadcast announcements. A broadcast can originate from another application, such as to let other applications know that some data has been downloaded to the device and is available for them to use, or from the system, for example, a low battery warning. Each application runs on its own dedicated virtual machine and its own single process that encompasses the application and its virtual machine, as shown in the figure. This approach, referred to as the sandboxing model, isolates each application. Thus, one application cannot access the resources of the other without permission being granted. Each application is treated as a separate Linux user with its own unique user ID, which is used to set file permissions. An activity is an application component that provides a screen with which users can interact in order to do something. Each activity is given a window in which to draw its user interface. The window typically fills the screen, but may be smaller than the screen and float on top of other windows. An application may include multiple activities. When an application is running, one activity is in the foreground, and it is this activity that interacts with the user. The activities are arranged in a last-in, first-out stack, in the order in which each activity is opened. If the user switches to some other activity within the application, the new activity is created and pushed on to the top of the backstack, while the preceding foreground activity becomes a second item on the stack for this application. The figure on the slide provides a simplified view of the state transition diagram of an activity. Keep in mind that there may be multiple activities in the application, each one at its particular point on the state transition diagram. When a new activity is launched, the application software performs a series of system calls to the activity manager. On create, does the static setup of the activity, including any data structure initialization. On start, makes the activity visible to the user on the screen. On resume, passes control to the activity so that the user input goes to the activity. At this point, the activity is in the resumed state. This is referred to as the foreground lifetime of the activity. During this time, the activity is in front of all other activities on screen and has user input focus. A user action may invoke another activity within the application. For example, during the execution of the email application, when the user selects an email, a new activity opens to view that email. The system responds to such an activity with the onPause system call, which places the current running activity on the stack, putting it in the paused state. The application then creates a new activity, which will enter the resumed state. At any time, a user may terminate the currently running activity by means of the back button, closing a window, or some other action relevant to this activity. The application then invokes onStop0 to stop the activity. The application then pops the activity that is on top of the stack and resumes it. The resumed and paused states together constitute the visible lifetime of the activity. During this time, the user can see the activity on screen and interact with it. If the user leaves one application to go to another, for example by going to the home screen, the currently running activity is paused and then stopped. When the user resumes this application, the stopped activity, which is on top of the backstack, is restarted and becomes the foreground activity for the application. The default allocation for processes and threads to an application is a single process and a single thread. All of the components of the application run on the single thread of the single process for that application. To avoid slowing down the user interface when slow and/or blocking operations occur in a component, the developer can create multiple threads within a process and/or multiple processes within an application. In any case, all processes and their threads for a given application execute within the same virtual machine. In order to reclaim memory in a system that is becoming heavily loaded, the system may kill one or more processes. As was discussed earlier, when a process is killed, one or more of the activities supported by that process are also killed. A precedence hierarchy is used to determine which process or processes to kill in order to reclaim needed resources. Every process exists at a particular level of the hierarchy at any given time, and processes are killed beginning with the lowest precedence first. The levels of the hierarchy, in descending order of precedence, are as follows. Foreground process, a process that is required for what the user is currently doing. More than one process at a time can be a foreground process. For example, both the process that hosts the activity that the user is interacting with, activity in resume state, and the process that hosts a service that is bound to the activity that the user is interacting with are foreground processes. Visible process, a process that hosts a component that is not in the foreground but is still visible to the user. Service process, a process running a service that does not fall into either of the higher categories. Examples are playing music in the background or downloading data onto the network. Background process, a process hosting an activity in the stopped state. Empty process, a process that doesn't hold any active application components. The only reason to keep this kind of process alive is for caching purposes, to improve startup time the next time a component needs to run it. As was mentioned in Lecture 2, Mac OS X Grand Central Dispatch, GCD, provides a pool of available threads. Designers can designate portions of applications, called blocks, that can be dispatched independently and run concurrently. The operating system will provide as much concurrency as possible based on the number of cores available and the thread capacity of the system. Although other operating systems have implemented thread pools, GCD provides a qualitative improvement in ease of use and efficiency. A block is a simple extension to C or other languages, such as C++. The purpose of defining a block is to define a self-contained unit of work, including code plus data. A sample example of a block definition is on the slide, x equals and so on. A block is denoted by a caret at the start of the function, which is enclosed in curly brackets. The sample block definition defines x as a way of calling the function, so that invoking the function x would print the words hello world. Blocks enable programmers to encapsulate complex functions together with their arguments and data, so they can be easily referenced and passed around in a program, much like a variable. Blocks are scheduled and dispatched by means of queues. The application makes use of system queues provided by GCD and may also set up private queues. Blocks are put onto a queue as they are encountered during program execution. GCD then uses those queues to describe concurrency, serialization, and callbacks. Queues are lightweight user space data structures, which generally makes them far more efficient than manually managing threads and locks. Depending on the queue and how it is defined, GCD either treats these blocks as potentially concurrent activities or treats them as serial activities. In either case, blocks are dispatched on a first-in, first-out basis. If this is a concurrent queue, then the dispatcher assigns F to a thread as soon as one is available, then G, then H. If this is a serial queue, the dispatcher assigns F to a thread and then only assigns G to a thread after F has completed. The use of predefined threads saves the cost of creating a new thread for each request, reducing the latency associated with processing a block. Thread pools are automatically sized by the system to maximize the performance of the applications using GCD while minimizing the number of idle or competing threads. In addition to scheduling blocks directly, the application can associate a single block and queue with an event source, such as a timer, network socket, or file descriptor. Every time the source issues an event, the block is scheduled if it is not already running. This allows rapid response without the expense of polling or parking a thread on the event source.